In today's video, we are going through Art of Electronics exercise 2.10 or 2.10, and in this exercise we need to calculate the current source power dissipation. We looked at this circuit in more detail on exercise 2.9, so if you haven't seen that video, please go check that out before you go through this video, as that's going to be very important for this question. So the question says, suppose you want a 10 milliamp current in the preceding problem, the preceding problem being exercise 2.9. Then we are asked to calculate how much power is dissipated in the series resistor and how much gets to the load. Now, if you remember from exercise 2.9, I'll do a quick recap. We basically calculated that we need at least 1000 volts power supply to maintain a 1% accuracy for the current source. Obviously, the question was trying to show that doing this circuit is not very practical for current sources. So we need to calculate the power dissipated in the series resistor, and then we need to calculate how much power gets to the load. So this is the circuit that we looked at in exercise 2.9. We have a series resistor here and we have some load, and we have our 1000 volt power supply from the question previously. Now we want a 10 milliamp current, and we need to calculate how much power is dissipated in this resistor and how much power is dissipated in this load. So first of all, let's go to the calculations. So the power dissipation of the resistor depends on the voltage drop across that resistor and the current going through it. Obviously, we'll know the current going through it as we are asked for 10 milliamp, but we need to calculate the voltage drop across the resistor. We also need to calculate the resistor value as well. So the voltage across the resistor is going to be Vs minus V load. Obviously, our load varies from 0 volts to 10 volts. And the power dissipation of the resistor is going to be I squared, so that's the current through the resistor, times the resistance itself. Next, we can determine RS. So for worst case scenario, the maximum voltage drop across R basically occurs when the load voltage is at 0. So basically all the power supply, so the 1000 volts, is dissipated across the resistor. So that gives us a resistor value of 100 kilo ohms. And obviously we know the current going through it is going to be 10 milliamps. Now that we know the resistance value and we know the current value, we can also calculate the power dissipation across the series resistor as well. So we have our RS from the previous slide, and we can calculate the power dissipation of the resistor with the I squared R equation we spoke about before. Now we know I, so that's 0.01, and we know R, which is 100 kilo ohms. So if we plug in our I and R into this equation, we get a power dissipation of 10 watt for the resistor. The load power dissipation is a little bit easier to calculate, because we know the current and we know the voltage. So we can basically use P equals VI, and we are going to get maximum power dissipation when V is at maximum, because the current should be fixed to 10 milliamps. Therefore, plugging the numbers into P equals VI, we get a power dissipation of 100 milliwatts. So what this question is telling us is that for a 10 milliamp current source, the series resistor, which is basically not our load, is going to get 10 watts of power. But the actual thing that we care about, which is the load, is only going to get 100 milliwatts of power. Now, if you do the maths, you can calculate the efficiency of this circuit is roughly 0.1%, which is very, very low. So you wouldn't want to use this circuit in any real applications unless your source current or the current source that you're trying to produce is very, very, very low. Otherwise, it would not be worth it. So to prove that the circuit that we are talking about is accurate, the next thing I'm going to do is show you the LT Spice model of this and just show you that, it is producing 10 milliamps for both conditions and that the accuracy stays within 1%. So let's switch over to LT Spice now. So for the LT Spice circuit, we calculated that we need a voltage source of 1000 volts. We need a series resistor that is 100 kilo ohms, and our load varies from 0 volts to 10 volts. So what we can do is replace this with a power supply, or we can basically put a resistor in here. I'm going to replace it with the power supply. So basically I'm going to copy this power supply and add a pulse with a initial voltage of 0 volts and a maximum voltage of 10 volts that we need, and I'm going to set the rise time and the fall time to be 1 second. The T on and T off doesn't matter, so I'm just going to do 2 and 4 seconds basically, and I'm going to run the simulation for 1 second. So we should get the load changing from 0 volts to 10 volts over 1 second. I just need to fix this because I placed the name in the wrong place. So R1 here and 100 kilo ohms over here. You can see I've got the 1000 volts here, so 1000 volts. Now let's look at the current through this. You can see it starts off at 10 milliamps. Ignore the direction, that's just because of this arrow here, and it goes down to 9.9 milliamps. So you can see that it is within 1%. And let's look at this load, which is basically going from 0 volts to 10 volts. So you can see as you change the load voltage from 0 to 10 volts, our load current, or the current through the load, doesn't change by more than 1%. So the current source that we have calculated for this question is accurate and obviously works like we need to. The next thing we can do is basically calculate the power dissipation on the resistor. So if we click on the resistor itself when the simulation is running, we get the current through the resistor. And if we click around the resistor by click and holding the mouse button down, we get the voltage across the resistor. Now, if I right click on the graph name over here, so the legend, and I type in IR1, which is the current through the resistor, I can basically get my power dissipation on the resistor. You can see the maximum power dissipation in this resistor is 10 watts and the minimum power dissipation is 9.8 watts, basically when the load voltage is at its highest. We can do the same thing for the current source over here. So we can look at this voltage, which is V, and the node is called N002. You can give this node a name if you want to. And the current through that is IV2. So I'm basically going to take that voltage at the top and multiply by IV2, and you can see the maximum power dissipation on this is 100 milliwatts, like we calculated for the question. In LT-Spice, we can also calculate the efficiency like we did in our question. So I'm going to basically get the power dissipation for the resistor as well and delete this current, and I can do this divide by this, and that would give me the efficiency for this circuit, which we calculated as being 0.1%. So this is the load and this is the dissipation series resistor. So this is the useful power and this is the wasted power. So let's take this equation over here and put it down over here. So obviously we need to use brackets now because division. Now this is not going to be in percentage, so ignore that, but if you multiply the number by 100, it basically gives you your efficiency for the circuit, and obviously we calculated that to be being 0.1%. So hopefully you found that useful. If you have any questions, please let me know in the comment section below and I'll be happy to try and answer them. I want to take this opportunity to take some feedback from you guys, if you have any, obviously, for suggestions on what I can do for my channel. So if there's anything that you want to see in particular in terms of electronics or engineering, then please let me know and I will try to add that or make videos on those topics. At the moment, obviously, I'm still going through out of electronics and there's a lot more to go through. I do have the audio amplifier board that I still need to kind of put together. Obviously, it's all designed and ordered. And I also have the IMU USB board that we designed in one of the videos before. So I will be going through those. I plan to go into detail about how I2C works and things like that. So, break it down, look at the signals on an oscilloscope and things. So hopefully that will be quite interesting. But yeah, if you have any suggestions for me, please let me know in the comment sections and I'll think about adding those kind of videos to my channel. So thank you for watching today. Don't forget to like, comment and subscribe if you enjoyed the content. And if you want to support this channel further, you can basically become a member or share this video with your friends. Thank you for watching. Bye for now.